All right, peeps. Yep, we're getting this thing rolling right here. Yeah, let me do this. Let me do that. Sorry. Hey, if any of you are on this, like with a Mac, like cool thing, you can do this with your phone too. Go down here, go to focus. You can set up different focuses, whatever you want. So yeah, I'm gonna do work for this one. I set up on a date. I set up droning. I'm going to do that right there until this evening. That way, if anyone texts me, it's not going to show up on my screen. So, yep. Okay, so, silly stuff like that. Yeah, let's do this and let's show. There's one thing I want to do, which is show, export, edit, Windows. Let's see. Open new location. Nope, not that. Clip assignment, writing. There's one that used to show tab, enter full screen, float on top. There we go. All right, so here we go. 2.3, biogeochemical cycles. So figure 3, the ecological footprint and biocapacity for selected regions, 2016. So if you look down here, the blue is the ecological footprint, the green is the biocapacity, just how much life that environment can handle, basically. And the ecological footprint is basically the cost of the amount of people we have living there. So if you look here, North America, because that's where I'm at right now. Damn! All right. That shows that you are living beyond the biocapacity. That is non-sustainable. Hey, South America, living below the biocapacity. That is sustainable. Very good. Non-EU Europe, living below the biocapacity. That is sustainable. European Union, not doing so hot. Looking like the American model. Yep, non-sustainable. Same thing for the Middle East, Central Asia as well. So Central America, Caribbean, yep. Asia Pacific, not doing so hot. Africa, still living above that biocapacity. Yep, more people than there are resources. So looking at this right here, identify one region shown in figure 3 that has an ecological footprint less than its biocapacity. Ding, 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 ding. All right, now after you've done that, outline one reason why a region whose ecological footprint is greater than its biocapacity is considered unsustainable. Yep, so it's basically state and then tell me why. Good. All right, outline one way in which a region can exceed its carrying capacity. Too many births. Yeah, so, yep. Productivity contributes to the biocapacity of land. Outline one climatic factor that limits the primary productivity of a region. Ooh, that one's good. Evaluate the use of the ecological footprint as a model. If this was a test question, because it says evaluate, they're looking for probably 3 pros, 3 cons, and 1 conclusion at the end. That would probably be one of those 7 to 9 mark questions. So, yep. Let's move on. Hey, define these for me. The answers are on page 154 to 155, or what you can do is Google them. Hey, if AI is out there, you can use that too. Use whatever service you want. Just make sure you get yourself a definition for these. You have biogeochemical cycles, stores, sinks, sources, carbon fixation. Biogeochemical cycles. First vocab word. Let's see what we get into with it. There's organic and inorganic. Basically, carbon and other elements are in plants, animals, but go into the soil when they die. So, yep. Ashes to ashes, dust to dust. Religious, but also still very much with science. Elements are in the organic phase a lot shorter time than the inorganic phase. So when you lock something up in a rock, it stays there a lot longer than it does in your body. So think about this, carbon in your body, right? Yeah, you're around for, we'll give you a benefit of the doubt, 100 years. Then you die, and that goes in the soil. Or if you're locked up as sedimentary rock, you're in there for thousands of years, maybe longer. So, yep. Major cycles are the water cycle, carbon cycle, nitrogen, sulfur cycle, phosphorus. We get into all these in this course with the exception really of like sulfur. I just don't really touch on that one much. Humans are impacting the cycles quite a bit, all the way around. Anthropogenic. If you know that, it means human activities. So, carbon cycles are in 4 storages: soil, living things, the ocean, the atmosphere. You're going to be in one of them. Remember, matter is not created or destroyed, it is just transported and transferred. So, cycles between organic and inorganic cycles. Fixed is when it's locked up. These are different terms you're going to have to learn. By photosynthesis and released by respiration. So photosynthesis locks it up, and released it by respiration. Just you breathing, you living your life, you using energy just to stay alive. Or released by burning of fossil fuels, which is another nasty thing we do. That's how you get, your gasoline engine, putting carbon off in the atmosphere. Through decay, respiration, and burning, carbon dioxide plus water vapor heat is released. Yeah, think about this. You go running down the sidewalk. Say it's after an ice cream truck. You're breathing hard. You get there sweaty. You're releasing heat off in the environment. You're also releasing water vapor. And you're also putting out their carbon dioxide. So, yep. Photosynthesis recaptures carbon dioxide and fixes it as plant matter for a while, and then it goes back. When the plant dies, it goes into the soil. So plants burned, used for food or decay, carbon is released again to the atmosphere. So if you're burning wood, say you got a Christmas tree, you threw it on a bonfire, which is kind of like nature's fire starter, by the way. You're putting off carbon off in the atmosphere. It's not as much as if you're burning fossil fuel, though. So carbon can remain locked up for a long time as coal or oil underground. Doesn't bother anybody under there. As soon as you burn it, it goes off in the atmosphere, creates an unbalanced system. So the unbalanced cycle. With humanity burning fossil fuels, how is carbon storage shifting? Where is there less and where is there more? So, interesting question. Yep. If you listened to me earlier, pretty much have the answer to that. Residence time. Average time an atom is stored. Coal, it is millions of years, unless mankind digs it up to burn for energy. Then, not so much. So, carbon stores. Organic, living plants plus animals. In death becomes fossil fuel. Yep. So, living plants usually become coal, I believe, and animals later on more likely to become oil. Could quote me, don't quote me on that, but just a standard. Inorganic, stored as sedimentary rock. So, yep, remember we talked about sedimentary rock earlier with carbon? Here you go. Blends in the ocean, makes up carbonates that are used in seashells plus coral as well. Enters into the soil, CO2. So those are your inorganic stores of it. When it's inorganic stored in the soil, it can be used by plants. When it's stored in sedimentary rock, not as much. So most carbon is, that's C is for carbon, by the way, is stored in rock. So limestone, coal, etc., locked up for millions of years. Also in the oceans. So carbonate, bicarbonate. Carbon is essential to life. You ever see science fiction movies where sending astronauts to space, Star Wars, Star Trek, stuff like that? They're always looking for carbon-based life forms. All right, again, carbon-based life forms. So, yep, just what they're looking for. Carbon flows. Let's get these going here. I'm going to move this down here for a second. We don't need that really big. We can minimize that. Yeah, right like that. I'll move my face up there. All right. So carbon flows. Organic is fast and the inorganic tends to be slow. The inorganic is like fossilization, combustion, dissolving. So combustion, you can make a case for it being slow. When you talk about this from the book, it might be talking about volcanoes, possibly. So this doesn't happen very often. Organic fast, photosynthesis. Oh, yeah. Get that? Sugar's rolling. Yep, lock up that carbon. So respiration. Yep, breathe it on out. Get rid of it. Feeding, defecation, which is a nice way of saying pooping. Death and decomposition. All those happen rather fast. I know we think death happens pretty fast. Put your body outside, unless it's like freezing, it's going to decay pretty quick. All things relative. So, the carbon budget. Where nature places carbon, tries to do it in a balance. Where humans place carbon, which is not in balance. The difference and imbalances. Keyword there, imbalances. Human in the carbon cycle. Nature balances the carbon cycle over long term. So when you start looking like weather and climate, climate is like long-term weather. Think of that a little bit with nature's relationship with the carbon cycle. It looks long-term. So nature has carbon enter the atmosphere with infrequent volcanic eruptions. That's the only way you're really getting carbon in the atmosphere in like a grand scheme of things, like with nature, one big event. So humans add carbon to the atmosphere consistently by burning fossil fuels. Look at our school buses that bring us to school. Look at our whole economy. It's really, without fossil fuels, it doesn't happen. We're probably back to an agrarian society, to be honest, where we're just all farming. Humans, so puts carbon on fast carbon flow. Pre-industrial revolution, carbon dioxides were 280 parts per million. You know that off of study of glaciers and just melting. 2023, hey, we're up to 414 parts per million ppm. So basically if you do the math out for that one, that's more than a 25% increase. So not good. Agriculture and forest systems in carbon. Forests plus farms can act as carbon sinks. Locking up carbon, basically. This is one of the reasons why forests are so important. They're not just important for biodiversity, important for other things as well. It helps restore the carbon balance, which is why reforestation, big thing. I'm looking to try to do it at our school. We'll see if we get some plans rolling off the ground. Helps restore carbon balance. Actions that help promote soil as a carbon sink. No-till farming. That's where you see like tilling of, let's see here. Farm tilling images. That's where you see these things where they all got like nice rows like that. That really helps the crops grow because it turns the soil. However, though, it also kicks up a ton of methane, CO2. So, not the best. Where were we? No-till. Crop rotation. You don't really want a monoculture where you're planting the same stuff every year in farm fields. Why? Because it sucks up all the nutrients. And then what you're left with is like really crappy soil. So you're better off having a crop rotation. Here in New England, you're better off having corn one year, and then maybe tobacco another, and then another year you're going to let it go to hay for farm animals or horses or whatnot. I'm just thinking outside the box. And then following year, those are pretty much the crops we raise here. Maybe the fourth year you let it go fallow. So, different things. Cover crops as well. So cover crops tend to be, let's take a look at those cover crops. Cover crops. Crops are plants grown to improve soil health and water quality between cash crops. So, just things in between. Let's see if we got an image. So, basically crops that in between your other crops. Interesting way of doing it. So, drainage of wetlands plus monoculture farming deteriorates soil. Same thing when you're burning rainforest as well. When you burn rainforest, the ground is like nice and bougie and fertile for a little bit, but it gets washed away and the soil doesn't stay fertile for long. So forests have absorbed 25% of human emitted carbon. So imagine without them, that's 25% more carbon we're putting off in the atmosphere. Forests are considered carbon sources if they release more carbon than they absorb. So think of it like with a forest burning. So if a forest is burning, it's a carbon source. If it isn't, it's a carbon sink because it's soaking them up. Forests are carbon sinks if they absorb more carbon than releasing it. So let's bring that on up right to about there. On average, an average round trip from New York City to LA emits 870 kilograms of carbon per economy passenger. An average red oak tree weighs 227 kilograms, but half of the weight is water. If Taylor Swift flies from New York City to LA and back, but plants a red oak tree, does this offset her carbon footprint, and by how much? So, yep, gotta do some math there. Or if you're in England, gotta do some maths. So, atmospheric carbon. It then goes into photosynthesis. Once it goes into photosynthesis, it produces biomass. Once it produces biomass and the plant dies, it becomes dead organic matter, which then goes back into the soil. For you are dust, and to dust you shall return. Genesis 3:19. Ashes to ashes, dust to dust. The carbon cycle of forests is a dynamic process. So above ground, you have most trees' carbon stored as woody biomass. Some of it's also stored as leaves that become soil. The remaining carbon is released back into the atmosphere via respiration and decomposition when it dies. Woody biomass is stable. It's long-term. It decomposes slowly. That's why one of the reasons too why when a tree falls in the forest, you're kind of good to leave in it because it soaks up quite a bit of water. I've heard that it actually is more likely to get rid of, or not get rid of, but is a hindrance to wildfires. Just what I've heard. Roots prevent the erosion of water too and washing away of soil. So a lot of the climate storms we're getting, where with a lot of massive amounts of precipitation, rain, keeps the soil where it is instead of washing it away and turning our rivers nasty and brown. Young trees, respiration loss of carbon is low. Roots prevent the erosion. Here, let me try something here. Yeah, I'll add some light to my face there. Most carbon is fixed to biomass. Yeah, we like that. I got a little emoji down there. That means like young trees. Yeah, we're sucking up that carbon. Big carbon sinks. Old trees, the respiration increases because they need to maintain all that big biomass. That means there's going to be more carbon it puts out in the atmosphere. Does not lock up as much carbon. Reaches a steady state, no more carbon's added, just maintained. So carbon input is photosynthesis equals the carbon output, carbon respiration. On average, it takes 90 to 120 years for this to happen. What do you think we should be focusing on more right now? Planting young trees or saving old growth forest? Puts things in perspective. Think about that with sustainable logging. Yep. Not talking clear cutting. So, let's take a look at this down here. Natural forest and coniferous forest monocultures in Japan. So, coniferous forest monocultures, natural forest. Ooh, okay. So what they mean by coniferous forest monocultures, they're basically planting one type of tree. All right? That's not the way nature really intended it. Hey, we'll take it, but could do better. So it looks like the monocultures have grown. The natural forest have grown as well, but not nearly as much as those monocultures. Using figure 7b, distinguish between the trends for the natural forest and coniferous forest monocultures. Explain why coniferous forest monocultures have low resilience. Oh, yeah, exactly. So tell me why these ones, if something bad happens, they don't bounce back. All right. All right, let's take a look here. Oceans and carbon. Yeah. Sequester 25% in oceans and carbon. Sequester 25% carbon in the atmosphere. Sounds about right. Mostly surface ocean. We're pumping out more carbon than the ocean can absorb. Also, when you absorb the carbon, it just becomes acidic as well. Result equals ocean acidification. This messes up your coral and your shellfish. Right now, the freshmen are doing this thing where they're getting some seashells. Ate some stuffed clams with the wife the other night. Tasted lovely. She loves them, and keeps me out of trouble. So happy wife, happy life. But the seashells we ran through the dishwasher, and then after that brought them to school and gave them to the science teachers for freshmen. Science teachers smashed up the shells, put the different pieces in different types of acid. The more acid there is, the more the shells deteriorate. Keep that in mind for coral reefs. The more carbon the ocean absorbs, the more acidic the ocean is. The more acidic the ocean is, the more the coral reefs deteriorate. So that's basically it. Oh yeah, problem with the shellfish too. So alleviating the effects of humans on the carbon cycle. First equals products that produce less greenhouse gases to make. So renewable energy, big time. The lights that I just turned on, powering them with solar power is probably a good idea. Also, wind power is another one, hydroelectric, although that one can be a little bit dirty. Other forms of renewable energy as well. Second, reduce fossil fuel burning. If you do it with renewable energy, it takes a big chunk out of that. To be real, energy use is only going to increase. Why I say this is because growing up, the house that I grew up in, you had one electrical outlet per room. I challenge you, look at your household that you live in. Do you have more than one outlet per room? Reason why there's only one outlet per room back in my day, we didn't have iPhones. We didn't have air conditioners. Barely had a fan. All right, you had one TV for the whole house. So you didn't need a whole lot of electricity. Now we use a lot more of it. So, yep, it's only going to increase. Third, biological sequestration, room for growth. Forests lock up carbon 12 times more than cropland does. So yeah, you can grow crops or you can grow trees. Trees will soak up 12 times more carbon than the crops ever will. Afforestation, planting of trees where trees have not grown in 100 years. All right, so at our school building, it was like originally swamp, but I'd love to afforest the land, get trees growing back there. I don't think it's been 100 years since they've been gone, but I think it'd be good just to throw a few back up there. Fast-growing trees can be grown, used for paper, burn biomass for energy, replant. So in a way, it gets this like whole system going. So they do this right now for Japanese knotweed, I've heard in England. Japanese knotweed is an invasive species. It grows like you would not believe. You chop it down and it's back the next day practically, it seems like. So, and it locks up carbon pretty darn good. So you could grow it, burn it, carbon goes off in the atmosphere, grow it again, it soaks up the same dang carbon. So, yep. Reforestation equals reestablishing trees on deforested land. So that would be more like if we planted trees in the middle of our playing fields, which we're probably not going to be able to do, but there are some spots where we could do some reforestation. So forest management is selective harvesting instead of clear cutting. Planting fast-growing trees. Yep. Fourth is artificial carbon sequestration. Ooh, this is like Mobil Oil, isn't a bunch of other companies are really into this one, which I'm okay with. Why? Because it's not going to be one thing. You can't put all your eggs in one basket. Differentiation, diversification, all these words is like basically safety in numbers. You got to have different ways of going about it. So carbon capture and storage, CCS. Burn fossil fuels, collect emissions like carbon dioxide, store underground instead of the atmosphere. Can also be used when stored underground to push more oil gas out for human use. Yep, we'll show a picture of this later. So basically what you're doing is burning, say this is a chimney. Yep, you collect natural gas, you burn it, but instead of the smoke going and carbon going right out the chimney, you basically collect it, go pump it down into the ground, where you're then storing that carbon dioxide underground. Thought is when you pressurize it long enough that it basically stabilizes underneath there and it's not going off into the atmosphere. So, all right, let's get down to this one. Bioenergy, carbon capture and storage. Grow plants. Hey, they absorb carbon dioxide, right? Yep. Then you cut down plants, then burn them. Remember talking about Japanese knotweed? Collect the emissions like carbon dioxide, store underground, repeat by regrowing plants. So this right here is a cool way how you can make a huge dent in the atmospheric CO2. It's an idea they came up with. Basically, so you you cut down plants, you burn them. Instead of the CO2 going off the atmosphere, you collect it, pump it underground. So now it's stored underground, and then you replant, and then when you replant, it absorbs even more CO2 from the atmosphere. So in a way, it's taking CO2 from the atmosphere and transferring it underground. It takes time to do it, but it's really kind of a cool idea. Graphene production actually uses carbon dioxide. It's another way you can do it. So yeah, it's not ideal, but working on it. Engineered molecules using atmospheric carbon to make molecules. I'll be honest with you, I don't know about this one. It's at the time of this, it's really the first time I'm hearing about it. I'm gonna have to read a few more articles and stuff about it. Being honest with you, sounds rather space agey to me, but then again, AI did too, and now everybody be using it. So a little more on the carbon cycle, more on carbon stores, yeah, just like that. Lithosphere, underground earth stores. Yep, that's what the lithosphere means. Limestone, largest store of carbon. So most is fossilized remains of dead coral and seashells. Yep. So calcium carbonate. Limestone's kind of brittle though, and it with water it just deteriorates over time. Interesting enough, and definitely with acid it does. So acid rain, no bueno for it. Fossil fuels. So coal, partially decomposed plants. Oh, I was right. Oil plus gas. And I think they mean natural gas, not gasoline. Particularly decomposed animals. Does it say particularly? I think it says partially. There we go. Partially decomposed animals are 10 to 180 million years old. So, yep, that's about high. Take millions of years to form, and humanity burns them in an instant when we just go driving down the road. Making my way downtown, driving too fast, hitting the gas, doot. All right. How long carbon stays in systems? Limestone, hundreds of millions of years. Yep, locked up there. Atmosphere, about 5 years before it gets knocked down. In the biosphere, about 13 years. And then the ocean's 350 years before it gets pressurized back into like limestone or like oil or gas, something like that. Peat as a carbon sink. Ooh, yeah. Stores huge amounts of carbon. Partially decomposed, decaying vegetation in swampy water. That's what peat is. So it's too acidic, plus without air to decompose. So that's really why, you don't go, putting a body in a peat bog. It's not going to decompose, you're going to get caught, all that sort of stuff. Peeps historically would burn peat for heat or to cook, but that puts it out into the atmosphere. And it puts tons of carbon out in the atmosphere. Peeps would also drain peatland and then plant crops there because it's a big time fertile. Yep. No longer carbon sink though. That's a problem with it. Peatland destruction is most common now in Southeast Asia, where this is what they're doing about draining the peatland and then using it for farming. Methane, CH4, burning fossil fuels releases it. Is a greenhouse gas, traps more heat than carbon dioxide. Little known fact about it. So yeah, methane, cow farts, is worse for you than CO2 as far as global warming. In the atmosphere for 10 years, then oxidized to CO2. So even after 10 years in the atmosphere, it just gets transferred to carbon dioxide, which is still a greenhouse gas. 40% is natural, 60% of it is human caused. Yep. I don't know if they put cows in there as human cause. Technically, that would be natural, but the way we eat hamburgers and get milk, that might be anthropogenic. So, yep. All right, let's talk a little bit about nitrogen cycle. Bacteria are essential. So for 3 stages, there's the fixation, nitrification, and denitrification. Nitrogen is essential for life, for protein building. You need them for making amino acids. Organic stores of it are proteins, amino acids, DNA. When you think of it that way, without nitrogen, without nitrates, you don't have DNA, deoxyribonucleic acid. So inorganic stores: atmosphere, ammonia, nitrates, nitrites in soil plus water, sedimentary rocks on the ocean floor. So that's just where you're going to find nitrogen. Yep. Page 166, or Google nitrogen fixation, nitrification, denitrification, decomposition. Yep. All that sort of stuff. Yep. Okay. Just want to read this for a second. Nitrogen fixation. Atmospheric nitrogen converted to ammonium ions by bacteria living in the soil. Yep. You can do it. I can never pronounce this word. I'm so sorry. Rhizobium bacteria living in legume root nodules. They're a symbiotic relationship. Cyanobacteria in the soil and water. Lightning oxidizes nitrogen. Haber process. This is something man created. It's basically an industrial way of making nitrogen fertilizers. We use iron for it. Name a country that makes a lot of nitrogen fertilizers. Russia, I believe. Nitrification. Nitrifying bacteria converts ammonium to nitrates. So, yeah, nitrifying bacteria basically converts ammonia to nitrates. Nitrobacter convert nitrates to nitrates. So if you get those two together, you're going to be able to produce nitrates from ammonia. Denitrification. A denitrifying bacteria reverses the whole process and releases nitrogen into the atmosphere. Waterlogged plus anaerobic environments. That's basically what does it. So swampy swamps, peat, something like that. Let's take a look down here. Decomposition supplies more nitrogen to soil than fixation. Insects, worms, fungi, bacteria, all that sort of stuff. Assimilation, living things take in nitrogen, use it to build bigger molecules. Nitrogen becomes amino acids, then becomes proteins. Example of this thing would be DNA, just with human beings and others. So natural nitrogen fixation. Alfalfa plus clover are best nitrogen fixing plants. Interesting enough too, alfalfa and clover, you will have wildlife loving you. You'll have deer visiting your yard. You will have bunnies. Actually, a lot of hunters, they'll plant alfalfa fields and clover. Why? Because they're not out there like with a bow and arrow trying to bag Bambi, but basically they're trying to get Bambi to live through the winter. And basically if you have a healthy deer, that's better for the population than an unhealthy deer, in which case they're going to die and they won't make it through the winter. So, yep. A lot of plant growth is limited to lack of nitrogen. So nitrogen is just like, oh yeah, feeling good, Rhizobium bacteria is mutualistic. Okay, so mutualistic is a better term for, I guess, than symbiotic. Legume plants give the bacteria sugars from photosynthesis. So the bacteria gets something out of this. Now, the bacteria then fixes the nitrogen to the root nodules and gives it to the legume plant, which then the plant is just like, oh yeah, now I got my my stuff to build proteins and build. So, yep. Cereals don't fix nitrogen, so need to have it added. One more reason why growing cereal in the Midwest is not as helpful as beans. So, why do so many Midwest farmers grow soybeans? Use AI or Google to answer this one. Oh, yeah, let's get that in blue, though, all right? Let's get that right here. Oh, shoot. Undo that. Yeah, we're going to highlight that one. Move that one down here. Highlight that. Blue. Bang. All right. Good. Why don't I leave that up there for a little bit? Why do so many Midwest farmers grow soybeans? Use AI or Google for that. So it's interesting enough. It goes into financial sustainability right now. Interesting stuff. Denitrification happens in waterlogged anaerobic conditions. Nitrogen washed away by leaching. Insect eating plants process insect nitrogen and then put it in lakes or ponds. The other thing is when it gets washed away or leaching, it goes down into ponds. Then you got nitrates in ponds, and you've got eutrophication, or you can have algae blooms out in the ocean, stuff like that. Rather nasty. Artificial nitrogen fixation is the Haber process. Remember I talked about it? It's an industrial process that uses high temperatures plus pressure and an iron catalyst to speed things up. Turns nitrogen from the air and hydrogen from methane into ammonia. So, yep. Sold to farmers as ammonium phosphate, nitrate, or sulfate. Yep. And helps your crops grow. Half the world population relies on food from this process. There's other ways of getting nitrogen in the soil that are more organic, more old school, but this one here gets results. So, advantages: ammonium nitrate has a lot of nitrogen. Nitrogen boosts crop yields. Disadvantages: it ain't cheap though. Nope, they don't do it for free. Inefficient because only 15% of the gases actually get combined. The rest are just reused again until they it's like keep trying to break that threshold, and then they just keep recycling the gases. So it uses 3 to 5% of the natural gas supply and produces 1.4% of the carbon emissions. So yeah, you are putting out quite a bit of carbon when you're doing this. So maybe you can offset that if you're a farmer by other ways of plant growth, and maybe using no-till soil, something like that. Humans in the nitrogen cycle. Humans produce nitrogen fertilizers from atmospheric nitrogen. Apply it to farm field soil. Little's taken up by plants. Most is washed away by ponds, rivers, and then the ocean. You gotta be careful if you're off in Vermont too, because one of the things they'll do is they got tons of cow poop up there. Think about it. The biggest employers up there are probably Cabot Cheese and Ben and Jerry's, which makes ice cream. So you got quite a bit of dairy farms off in Vermont, so you got quite a bit of cow poop laying around. Cow poop is great for spreading on your fields. It's got a lot of nitrogen in it, so you're going to be able to grow great corn. The only problem is you lay it out in your cornfield, and then the rain comes, it goes washing away into the creek, and then the nitrogen gets washed away with it. Then you got algae blooms in the ocean, you got nitrification in your lakes, ponds, all that sort of stuff. So, yep. Creates algae blooms and eutrophication. Basically, it's easy for humans to unbalance the cycle. So, humans, we eat plants plus animals, then piss out the nitrogen we get from them. So, nitrogen piss then goes to the waste management, then to the rivers and the oceans. Fertilizers from the Midwest farms go down the Mississippi River to create a dead zone in the Gulf of Mexico. Less shrimp are caught there, and a lot of it's got to do with a lot of the nitrogen we put on the farm fields in the Midwest. So, fertilizers used in growing oranges in Florida. Ooh, this is nasty. Heard from a captain once I was fishing with, you'll never beat big citrus. The industry down there in Florida, better off fighting Mike Tyson in the ring. You're probably going to last longer. So, fertilizers used in growing oranges in Florida runoff helps seaweed grow in the Sargasso Sea. Makes the beaches nasty. If you want to see it, Sargasso seaweed beach. Yeah, all this stuff on the beach. Imagine you go your tropical paradise like this in Puerto Rico, and this is what you see. This is not what you signed up for, mijo. I know. I no quiero. So, yep. So that's one of the issues we have with it. Whereabouts were we with this? Yep, Sargasso makes beaches nasty. Ocean, dead zone. Talk about above. Yep. Talked about this above just with the Mississippi River. Fertilizers from the Midwest run down the Mississippi River to Gulf of Mexico. Creates a dead zone off in the Gulf of Mexico where your shrimp catches are a lot less. So the air pollution, nitrogen oxides emitted from burning fossil fuels damage the respiratory system. Don't have to be a rocket scientist to figure that one out. Ozone depletion. Nitrous oxides react with the UV light at high altitudes and break down the ozone. More about this in chapter 6, but it's pretty nasty. Yep. Ooh, I got one there. I should probably move my face way up in the corner again. Good. Whereabouts was I? Yeah, we'll go right here. So, nitrogen oxide lasts 120 years in the atmosphere, so it's not going away anytime soon. Not in my lifetime, probably not in yours either. Climate change. Nitrous oxide is a greenhouse gas. Yep. Traps heat. Traps heat 300 times more than carbon dioxide, more than methane then too. So, rather nasty about it. So, soil acidification. Nitrates not taken up by plants combined with calcium plus magnesium. The result is acidic soil where plants have trouble growing. So, yep, plants don't like that acidic soil. Most of them don't. There's a few that do, but in general, rule of thumb, not really. Planetary boundary for biochemical flows. So, the future of nitrogen use by human activity. We can use renewables to help input of the Haber system, but output waste will continue to act as pollution. Remember, it's like an engine, input versus output. So you haven't figured out a solution for the output yet. We need a more efficient way to delivering fertilizers to plants. Rhizobium there, that nitrogen fixating bacteria, is kind of interesting to me. Another need would be a global agreement to reduce fertilizer use. So, yep. Or just relying less on the Haber process too. That would help out quite a bit. So, yep. Oh yeah, and that's 2.4. Oh shoot, you got a preview of it. All right, sorry. All right, everybody. My best. Later. Bye. All right, let's see how I stop this thing. We're going to go here. Uh-oh.